Chapter 1.5, More on Slope. So in this chapter, we will be covering some stuff about linear functions. So you'll notice that we skipped chapter 1.4. 1.4 goes over the basics of slope and finding y-intercept and graphing linear functions, etc. That is, we skipped that chapter because it is something that is covered in depth in our algebra courses. So if you are rusty on it, then I really encourage you to go back and review that chapter because it is something you're going to need to know how to do, even if we're not covering it in depth here. So instead, in this chapter, we'll be talking about specifically parallel versus perpendicular lines, interpreting a slope as a rate of change, and finding a function's average rate of change. But because we skip over chapter 1.4, I want to make sure that you guys are at least familiar with slope. So that this is a review or a reminder of how slope works, but it's going to be very brief and quick because, again, it's not something that is really covered by this chapter. It is something you're expected to come in knowing or spend the time to refresh yourself on if you don't. So the slope of a line measures the steepness of its increasing or decreasing. We calculate slope in the following way. Slope is equal to rise over run, where we can say rise is the change in y and the run is the change in x. So in this case, if I pick 2 points on this line, for example, the points I've picked are here and here, then the change in x, the run, I am moving from here to here, so I'm running 1. And the change in y, how much I have moved up, is 30. So we can say our slope would be the rise of 30 over the run of 1, specifically 30 miles over 1 hour using the units that are here. So our slope is 30 miles per 1 hour, 30 miles per hour. No matter what 2 points I picked on this line, if I had picked this point here and this point up here, yes, I would have a different rise and a different run, but the fraction itself should simplify. So this might be a run of 2 and a rise of 60, but 60 over 2 is 30. So we would still end up with the same slope no matter what 2 points you pick. Similarly, we can calculate slope using 2 points if we don't have a picture to work from. So the slope equation, which you will definitely need to know, is y2 minus y1 over x2 minus x1, where y2, x2 is a point and x2, y2 is a point and x1, y1 is another point. So here, from this table, I have picked 2 points. It doesn't matter which 2 I pick. It doesn't matter which is 1 and which is 2. I just happen to go in order. So when we calculate the slope using these 2 points, I would take 160 minus 80 over 4 minus 2, which is going to simplify to 80 over 2, which is 40, specifically 40 miles per hour. So remember, when you're doing this, you still want to pay attention to those units if we're given them. So hours and miles, so at the top is miles, the bottom is hours. So we get miles over hours, miles per hour. So 40 miles per hour is our slope. Can also make note that horizontal lines have a slope of 0. So every horizontal line, every line that is just a flat line has a slope of 0 because the change in y is 0. We have not changed our y value. No matter what x is, x can change however much we want. Our y value has not changed. So our rise is 0. 0 over a run of anything would just be 0. But vertical lines, on the other hand, our run is 0. We have not changed our x value. There is no run, we just rise. So we would be dividing by 0 according to the equation, and we're not allowed to do that. So we say that the slope of a vertical line, of any vertical line, is undefined because we cannot divide by 0. Alright, so now that we have a general idea about slopes and how to calculate them, etc., define a couple special types of lines. So parallel lines are lines where we have two distinct lines with the same slope. Distinct meaning they are two separate lines. They're not on top of each other. So two distinct lines with the same slope are parallel, and if they're parallel, they have the same slope. So it works both ways. As soon as you know two lines are parallel, they better have the same slope. So here, if we calculate the slope of these two lines, both of them have a run of 1 and a rise of 3, so they have a total of a slope of 3 over 1. Both of them do. Even though they have different y-intercepts, these are parallel lines with the same slope. Notice that no matter what, because they have the same slope, they are never going to cross. So that's a special property of parallel lines, is that they never cross. They are the only type of lines that never cross. So all horizontal lines would thus be parallel because they're never going to cross. Every line like this is never going to cross each other. Similarly, all vertical lines are parallel to each other because they are never going to cross. So, for example, if you're given an equation like 3x plus 1, and we want to find a line that is parallel to that line but passes through a new point, negative 2, 5, how do we do it? Well, we start by saying, okay, it's parallel, so we know what the slope is. The slope has to match the slope of the first line. So we have a slope of 3. So we put that in, and then we know this point, negative 2, 5. So if we know one point on a line and we know its slope, we can solve for the y-intercept, which gives us the equation of the line. So plugging in negative 2, 5, we get 5 equals 3 times negative 2 plus b, and then we do some quick arithmetic here, and we can add 6 to both sides to get a total of b equal to 11. And so, once we know what b is, we have an equation, y equals 3x plus 11, and we're done. We can say this line, our answer, is indeed parallel to the original because they have the same slope. But the other type of special line we have is called a perpendicular line, or a set of perpendicular lines. So if the product of the slopes of two lines is negative 1, then the lines are perpendicular. And if two lines are perpendicular, then the product of their slopes is negative 1. So once again, it goes back and forth. Once you know they're perpendicular, then you know that the product of their slopes is negative 1. If you know the product of their slopes is negative 1, then they're perpendicular. One thing to note is this might be a more difficult way to say it than you may have heard in the past. So, really, when I say the product of their slopes is negative 1, what I mean is, and you may have heard this before, is that the slopes are opposite sign reciprocals. That's what gives us a product of negative 1. So, opposite sign reciprocal. So here, if we look at our graph, we can see these two are perpendicular lines specifically because they meet at a right angle. So we know that parallel lines never cross. That's their special property. Perpendicular lines, on the other hand, always meet at a right angle. That's a special property of them. So if they're meeting at a right angle, we know they're perpendicular. Because when they meet at a right angle, it gives us this special slope property. So it all kind of comes together that these all can be used to say the same thing. So if we look at these slopes, we have, for the green line, a fall of 1 and a rise of 3. So in other words, the slope would be negative 1 over 3, because fall of 1 is negative 1. Whereas for the blue one, we have a slope with a rise of 3 and a run of 1, so 3 over 1, or just positive 3. So it is the opposite sign, 1's negative, 1's positive, reciprocal, 1/3 versus 3 over 1. That's what a reciprocal is. So opposite sign reciprocal. So we can also say, because we know about this meeting at a right angle property, all horizontal lines are perpendicular to all vertical lines and vice versa. Because horizontal versus vertical, they're meeting at a right angle, even though the way I drew it maybe doesn't look like it. But we can see on our graph all of these grid lines, they're meeting at right angles. And so they are perpendicular to each other, even if it's hard to say they are the opposite sign reciprocals because one of them has that division by 0 and is undefined and all of that, but we can see that they present that property. Then, for example, if we wanted to write the equation of the line perpendicular to 3x plus 1, which we've seen before in the previous problem, and passing through negative 2, 5, now it's perpendicular, so we know, once again, how to find the slope. That is our first step. Slope is going to be the opposite sign reciprocal of 3. So this is positive 3, so we go negative 3, but then reciprocal negative 1/3. So just like it was in the graph. So we start from that slope of negative 1/3. Then we plug in our point, negative 2, 5, and we do some simplification. So this will be positive 2/3 plus b equals 5, and then we subtract 2/3 from 5, which, when we simplify, ends up being 13/3. So remember, 5 is 15/3 minus 2/3 is 13/3. And so we have our final equation of negative 1/3 x plus 13/3. Now that we have seen these special types of lines, we've dealt with general slopes and how to calculate them, let's talk about why is slope important to us? Really, I sort of already showed one thing about slope that you may have not thought about as much before. When I said the slope of those first graphs was 30 miles per hour instead of just 30. Well, I was representing the slope as a rate of change. A rate of change just describes how some output quantity changes relative to a change in an input quantity. In this case, if I input hours, I output miles driven, or whatever distance traveled. So miles per hour is a rate of change. Our units are output units per input unit. So in a lot of these word problems, you're going to need to think of slope as not just numbers, but also using their units. It's going to be very important that you remember to include units in these problems. But we are also going to see what is an average rate of change, because a lot of real-world situations, you're not always going to be driving exactly the same speed the whole time, etc. Things change as you go. So maybe you are driving down the highway and sometimes you're speeding up, but sometimes you're in traffic and you get somewhere eventually, but you really don't know how fast you were going the whole time. You know you changed a lot, but generally if someone asks you, well, how fast were you going, you wouldn't necessarily know. It changed. But with an average rate of change, you would be able to say, well, I might not know at any given moment how fast I was going, but I could tell you in general how fast I was going on average. And all you need to know is the time you left and the time you arrived. And the distance you traveled. That's how we would find your average. So the average rate of change is the total change of the output values divided by the total change in input values. We write that like so. And yes, this is more complicated looking than the previous slope equation, but it is exactly the same as the previous slope equation in concept. So I have written delta y over delta x. Delta is a Greek letter. It's the Greek capital letter, which is kind of like the letter D in Greek. But in math, capital delta just represents the words change in. So if you ever see a capital delta in a math problem, it just means change in. So the change in y over the change in x. Okay, so that's broken down. That's the same as it was before. Then f of x2 minus f of x1. All right. So remember when we defined function notation that y equals f of x, right? So in other words, f of x2 is the same thing as saying y2. And f of x1 is the same thing as saying y1. So in other words, we have change in y over change in x equals y2 minus y1 over x2 minus x1. It's exactly the same as it was before. We're just being very specific about what 2 points we're picking, and we're realizing that it doesn't have to be on a line. It can be on any what's called a curve or any graph that we're given. We can pick any 2 points. It doesn't have to be a straight line between them. So if I have, for example, a table of average gasoline prices in particular years, we can consider the cost a function of the year. Our goal is to analyze how the price of gasoline changes per year, but we can see that it's not changing by a constant amount. Between 2005 and 2006, it went up by 31 cents. Between 2006 and 2007, it goes up by 22 cents, and so on. So it's changing. But if I want to know something about what's happening in general, what's happening overall, then I would ask, well, what's happening on average? So we are going to find the average rate of change instead of just the constant rate of change that we're used to from linear problems. To do that, we take our equation, change in y over change in x, or in this case, change in c of x over change in x, which is c of x2 minus c of x1 over x2 minus x1. And I've just picked the 2 endpoints, because if I want to know what's happening on average between 2005 and 2012, I start from 2005, end at 2012. So x1 is 2005, x2 is 2012, and I'm going to plug these points in. So when I do that, I get my 2012 value is $3.68 minus the 2005 value of $2.31 over 2012 minus 2005. In other words, over those 7 years, we have gained $1.37 in our average gas price. So over those 7 years, we've gained $1.37 in our average gas price. So it's $1.37 per 7 years. But to simplify that fraction, by actually doing the division, we would then say that's about 20 cents per single year. So this is just the simplified fraction, this 20 cents per year, to give us what these numbers represent. Because saying 1.37 over 7 is our slope doesn't tell us anything. It doesn't answer the question. But if I want to know what's happening on average each year, I can say, on average, we're gaining 20 cents a year. That's information that's actually helpful to answering the question being asked. So now, when we're talking about rates of change in slope, it's very important to think about the context of the problem, the units being presented, and how we can format our answers to make sure we're answering the question being asked. So, last thing to talk about is just why is average rate of change the way it is? What does average rate of change represent, especially on a graph? So if we're given a graph, for example, here we have g of t. And I'm not going to tell you what this graph represents from a word problem standpoint. We just have a graph at this point. And I just want to find the average rate of change on an interval, a closed interval, -1 to 2. So to do that, I'm just going to look at these points at -1 and the point at 2. And if I want to know what's happening on average between them, I'm going to use my average rate of change formula. So I find those 2 points, so -1, 4, and 2, 1, and I will plug into the equation. So notice that -1 and 2 are my t2 and my t1 in this equation, and then 1 and 4 are my g of t2 and my g of t1. So when I do this calculation, and I apologize, this should say T1 here, so make sure when you're taking notes that actually does say T1. So that'll be g of 2 minus g of -1 over t minus -1. Okay, well g of 2 is 1, as we've seen right here, and g of -1 is 4, so 1 minus 4 over 2 plus 1 simplifies down to -1. But what does that -1 really mean? So that -1 is the slope of the line between these 2 points, because that's what we're calculating is a slope. Even though this graph is not a line itself, the average rate of change allows us to find the average slope between these 2 points. But how do I know it's the average slope? Well, if I look at what's happening between these. So first, its slope is pretty steep, but it's getting less steep over time, right? It is, when I say steep, I mean steeply decreasing. So remember, we know what decreasing versus increasing is now. So it's steeply decreasing, but then it's getting less steep over time until it ends up being pretty flat, and then we start increasing. So we went from a slope of this line. If I was just calculating the slope of this line, it would be something negative, fairly negative. Maybe it's -2 or something like that. And then over here, maybe it's -1 or something in that regard. Maybe it's -3/2. Here we might have -1/2, and then we have 0. And then, well, now we're getting positive, so that's maybe a slope of 1. And then here, a little bit even more positive. Maybe it's a slope of 2 now. Again, I'm being very imprecise here because I'm not actually calculating any of these slopes or drawing these specific lines, but the point is we can see that as we go around this curve, the slope of the tangent to this, it is increasing or decreasing by slightly more or less as you go. So on average, what happened? Well, on average, we did a calculation and we can say that the average change was -1 throughout what was going on. So you'll learn a lot more about how this works and why it works that way if you take calculus, but for right now, that's the gist of average rate of change, so make sure you know that formula and how to calculate it. So that's it for this chapter. Luckily, this one is a bit shorter, like I promised. They do get shorter than those first 2 chapters, so hopefully this one was easier to get through. But next, we will be going on to chapter 1.6.